Okay, in this last problem, number crunching and getting the answer is actually pretty easy. But it's probably more important that we think about it conceptually and try to put some meaning to the problem just beyond just number crunching out the answer. So when we're in class, I actually tried to demo this problem here. So the problem as given is that we have a 10 kilogram block that is placed on top of a 40 kilogram block, and we're going to pull on a string with a force of 100 newtons that's tied to the 10. But let's go off on a tangent here for a minute. What if this 40 kilogram block was like a big textbook? So we have this big textbook, and then I'm going to put this paperweight on top of the textbook, but on the bottom of the paperweight there's like this little rubber piece which gives it a little bit of friction. So I want you to think about in class, if we tied a string to the paperweight and I only pull on the paperweight, like what would happen? So for example, this could happen that maybe that little rubber thing has so much friction that when I pull on the 10, it like moves the block right along with me, or the textbook right along with me. Or it could be that there's so much friction between the book and the table that when I pull on the 10, I move the 10 and the 40 like doesn't move at all. Or it could be that there's a little bit of friction up here, there's a little bit of friction down here, and when I pull on the 10, maybe the 10 is moving faster in this direction, but the 40 like ekes forward a little bit in this direction. Or might the 40 even go backwards? Like, I don't know what's going to happen. And I guess that's my point, is sometimes you have this intuition of what you think is going to happen, but it's hard for us to picture what this frictional force is compared to this frictional force to know what would really happen. So in problem 6 on the handout here, it's even a little bit more complicated because they're saying that this is frictionless. So like in real life, I could not even like try to picture what would happen in real life because I've never pulled something on a frictionless surface like this. So we could come up with an answer that isn't even what we would think is going to happen. My point is that you have to draw your free body diagram and you have to trust your arrows and you have to trust your answer. And then once you come up with your answer, you have to like put some meaning back into that. So here we go. So we have a 10 kilogram block, a 40 kilogram block, and it says the coefficient of friction between the blocks is 0.3. The coefficient of friction between the blocks. All right, so if I pulled this with 100 this way, that tells me that friction has to be going this way. And so I'm going to calculate this frictional force. That's going to be equal to mu mg. And it says that mu is 0.3. The mass is only going to be the mass that's above it. So that's going to be 10. And this is 9.8. And that turns out to be 29.4 newtons. 29.4 newtons. All right, so knowing that, let's see what's going to happen. All right, letter A says, what is the resulting acceleration of the 10 kilogram block? So I'm going to draw a free body diagram of just him. So when I do that down here, I have a big 100 going this way. And I can see that I have a little friction going backwards, 29.4. And so now I'm going to do M net, or F net equals MA. So F net would be the 100 minus 29.4 equals M. His mass is 10. And I can solve for his acceleration. And his acceleration is 7.06 meters per second squared. All right, part B. What is the acceleration of the 40 kilogram slab? So we're going to draw a free body diagram of just him. And so when I draw the forces that are acting on the 40, the only force that's in my picture is that friction that's up here at the top. So I'm actually going to draw it up here at the top. And that frictional force is going to be 29.4. So F net equals MA. The only force that I have is 29.4 equals his mass times A, and his acceleration is 0.735 meters per second square. So I can tell that when I pull on this 100 with 100 newtons on the 10, that the 10 is going to go forward at 7.06, and that 40 is going to actually eke forward at 0.735 meters per second squared. So he's not going to quite keep up with the 10, but he will be moving forward slightly.